Hello, everybody. This is Derek Demeter with the Bueller Planetarium coming to you tonight. We have Sol. We are going to be looking at the sun. We got our fancy schmancy solar shades, and of course, I got my visor here to protect from glare. Joining me this evening, of course, as you know, is Justin Srill, the commander and communications officer.
What's going on, guys? It's good to be here and nice and sunny outside. No, it's pouring rain.
No, it's pouring rain. But you know what? It's always sunny inside, right? Especially when you got these lights shining on your face. Actually, it's really nice because normally got this light shining on my face. These sunglasses help. And of course, joining us tonight as well, as you know, is our telescope operator extraordinaire and looking pretty good in those shades, Frank Kane.
Aloha. Yes, I'm also wearing sunscreen tonight as well. You can't tell.
I mean, that computer screen is bright, so you got to be careful. When we were looking at the sun, which, is a big ball of UV radiation. So we're definitely going to talk about that. Actually, that's all we're talking about tonight is the sun. Yes, we're going to be exploring the sun tonight. You might be thinking, how are we going to look at the sun when it is, well, dark outside? But don't worry, it's because actually here in Florida, it is pouring rain. We are drenched with weather. We actually have a tropical storm off in the Gulf of Mexico heading towards the Mississippi states, Gulf states like Mississippi, Louisiana, and whatnot. And we decided, why not do a program tonight about the sun? We're in the sunshine state, even though it's raining. But we have some really cool footage that we've taken in the last couple of days, including some really cool images of the eclipses and other different events. Now, of course, for those that are joining in tonight, of course, Justin is our communications officer. Justin will be, for those that are on Facebook, will be, looking at that and making sure if you have any questions or comments, be sure to let us know some things that you are interested in asking. Tonight's program is a little bit more just a hangout. Let's talk about the sun. Let's show off some cool pictures. But we also would love to hear from you in terms of what you might be interested in learning about the sun. So so again, leave those comments in the Facebook Live, and we will do our best to answer those questions when they come in. All right, so fellas, I want to talk about, so tonight is the sun. And it's interesting when we do planetarium programs. It's actually pretty interesting when we ask the question, what is the nearest star to the Earth? We actually get a lot of questions answered with what, Justin? What we get a lot of questions that are usually answered with what?
Oh, geez. Well, it depends on what age group or even the adults sometimes. But we get everything from, the moon.
No.
Oh boy.
Yeah, that one's kind of interesting, but no, it covers the whole gamut, right? But the sun is obviously the closest to us, but sometimes it's interesting, when you really call it a star, people take a quick second and go, well, heck yeah, it is, right? I mean, I got a sunburn today, and my skin was burnt by a star. I mean, how cool is that?
Starburn.
Starburn. Right. That's actually what we should be calling it from now on, is starburn, I think. But so, yeah, the sun is kind of, it's one of those things where we don't mean it to be a trick question, but a lot of people overlook it. But of course, the nearest star to our planet is the sun. Our sun is a star. And during our third grade program that we do in the planetarium, we actually talk all about the sun. And Justin has a really cool a little diagram that he shows during the program on how our sun relates to everything. And actually during, when we're not in the pandemic, we actually have a lot of students that come out and we actually show them the size of the sun compared to other stars in the universe. And our sun is actually a very puny star. There are some much larger stars out there. And, we talked about some of them like Betelgeuse, Antares, even Polaris is larger than our sun. So most of the stars that we see in our nighttime sky are actually larger than our sun. Our sun is a yellow dwarf star. But interestingly, though, even though it's called a yellow dwarf star, the peak light coming from the sun is actually more green than yellow. Isn't that crazy to think that our sun, the peak light from the sun, is actually in the green wavelengths? So technically, our sun is a green star. That's pretty
One of
cool.
the
Now,
things I love to tell the kids is, when obviously they have very heavy eye protection, but the astronauts on the International Space Station, when you get out of our atmosphere, you take away that orange, take away that yellow that you automatically assume it is, and they say it looks like just a giant white snowball. Why is
that's
that?
right. So when you think of the rainbow, Roy G. Biv, all the colors of the rainbow, red, orange, yellow, green, blue, indigo, and violet, when we combine those colors together, we get what we call white light. So essentially, think of daylight. Think of at around noon, you have pretty much the peak of the sun. And actually, if you look at the sun in the sky, which I don't recommend doing, but if you had the ability to look at the sun in the sky at noon, you will actually see it. It actually looks white. It doesn't look yellow or orange. And so it's actually white. And if you go to the home improvement store like Home Depot or Lowe's or any of those places, and you look for those bulbs that say daylight, what color is that, right? Of course, you plug that in, and it's just bright, kind of bluish white, and that's essentially the true color of the sun. And but the peak brightness is still in the green, which I think is really kind of neat to think about. But yes, it's not even a yellow star if you think about it. It's a bright white star. So kind of an interesting thing when you think about it. Now, of course, we all seen beautiful sunsets, right? We've seen beautiful sunsets. Frank, what's happening with the sunset? Why does the sun look more orange, more red than we see at that time?
Well, like you said, the spectrum of the sun itself does span the entire visible range. So our eyes have evolved to see exactly, what the sun is putting out more or less. And it's actually curious why we're so sensitive to green light, because it does peak in green. But as the sun sets, it's going through the atmosphere at an angle. And what you're seeing is actually the particles in the atmosphere and the atmosphere itself scattering that light in such a way that only the red light is what's coming through. So the further down the sun comes in the sky, the more atmosphere it has to pass through between you and where it is, right? So the line from your eye to the sun just becomes going through a lot more atmosphere, and there's a lot more particles and molecules to scatter that light and make it appear red, even though it really isn't.
Now, have either one of you experienced the green flash?
I've tried. I've when I went on vacation in Hawaii a long time ago, like we had like perfect horizons over the ocean out there. And like, that's the ideal situation to see something like that, right? But
Right.
I have never been lucky enough to actually see it. Have you?
I have seen it 3 times at the
Damn.
Dry Tortugas National Park. And
Oh, nice.
by the way, if you ever want to see the most gorgeous sunsets in your life, go there. And each day, because of the seeing, the atmosphere was so still, you could right. Basically, what happens is at the very, essentially, tail end of the sunset, the curvature of the Earth, the atmosphere, it bounces the light through our atmosphere and allows for the green part of the scattering in the atmosphere that Frank was talking about to become visible. And I think it's super awesome that we can see that. And it's something that, if you have a chance to watch a sunset and you have a really super clear horizon, like, the beach or the ocean, maybe you're on a, cruise ship eventually when those actually go on again, you can actually see this happen, which is really super cool. Justin, have you seen the green flash?
I have not, but it's funny you mentioned that, because the APOD for in May, I think it was just a couple weeks ago, was the green flash of the sun, the moon, Venus, and Mercury, all captured by the same photographer. That's just unreal.
Do you have it? Can you bring that up, Justin?
Yeah, I think so. Let's see
All right.
here.
Yeah, I mean, we should show them this amazing photo. And if you're not aware, for those that are watching this, the astronomy picture today, APOD, it's actually run by NASA, is quite an amazing website. There's actually a lot of really cool photos that you can see, and there you go. There it is. So actually, stay up there for a second, Justin. So
Sure.
You can see on the left there, the sun. Can you see that light? The light from the sun is actually getting distorted by our atmosphere and allowing us to see that kind of greenish hue. Same thing goes with the moon. The moon's not as bright, so it doesn't show it as much, but essentially our Earth almost acts like a lens. It creates chromatic aberration, if you will. So it's really, really cool that we're able to actually see it. And I think this is absolutely amazing that this particular this photographer here was able to capture Venus and Mercury as well.
Yeah, and speaking as a planetary imager, Derek, and you encounter this whenever you try to take a picture of the planets when they're low in the sky as well, right? You get that sort of refraction going on where one side is red, one side is blue, and that's just the atmosphere acting like a prism on us.
Pretty much, yeah. So there are actually things that you can buy that actually correct that, but sometimes I actually enjoy it because it shows, from a teaching tool, it shows kind of how our atmosphere, we have an atmosphere. And so pretty nifty. So let's talk about something. So Justin, you have this really cool software that I've used a few times, a couple times in our previous star parties, but I think it's cool that, before we get into the photos and things like that, maybe we could take a little quick trip to the sun from the convenience of our home, right? So what we're going to be using here is we're using a software called Space Engine, and Space Engine will allow us to take a trip closer to the sun. Now, we got these super powerful solar shades. I'm actually going to bring that down a little bit. There we go. Got too much glare going on. Anyways, so here we go. We're getting closer to the sun here, and we might want to bring up the exposure just a little bit, Justin.
Sure.
So here we are at the sun, and the sun is just this big, super ball of plasma, just big, hot ball of plasma. And, people like to think of the sun as this big ball of a big light bulb, essentially, just big, big light. But it actually is this churning, bubbling, just constantly dynamic ball of hot plasma. And the surface temperature on the sun, which we call the surface of the sun, is called the photosphere. And that's actually what we're seeing here in Space Engine. We're seeing the photosphere of the sun. And when we look at the surface of the sun, you can kind of see almost this bubbling or boiling look to it. Kind of looks like graininess to it. Frank, what are we seeing here on the surface of the sun?
Well, we're seeing these sort of convection skulls of, the heat and stuff boiling out from the center of the sun there, which takes a really, really long time, by the way. But they have these sort of columns that come up and spread out when they get to the surface. And that's what causes these really weird and beautiful sort of honeycomb patterns on the surface of the sun that we see.
So if you were to take an animation of the sun, you would see it bubbling just like your pot of water at home. If you're heating a pot of water, you get these convection layers. Basically, all convection is the heat will heated material will rise. It will get higher. It will cool. It will get denser. It will sink back down, get reheated, and you get these layers of heating, cooling, sinking, heating again, rising, and this creates this bubbling effect that we see on the sun. But what's happening here as well is we're also seeing that the sun. Actually, can you pull back a little bit, Justin? Let's take a look at what we call the corona of the sun. The corona, not related to the coronavirus, but the corona is the outer atmosphere of the sun. And we can actually see that the corona is actually fluctuating because of the fact that the sun, being this big giant ball of hot plasma, is creating electromagnetic fields, or in this case, magnetic fields. And these magnetic fields are changing and turning and spiraling, and some of these magnetic fields get twisted up, just like telephone wire or holiday lights. If you're, how many do either of you guys put up holiday lights in your home? You notice that every year you could put it as organized as you want. You open that box, and those holiday lights are tangled up, and you're just like, right? You're just trying to untangle these things. That's what's happening to these lights, or the magnetic fields. They're tangling up. Some of them actually puncture the surface of the sun, and they actually reveal those convection cells that Frank was talking about. And Justin, what do we call those that are these cooler areas that are exposed, caused by magnetic fluctuations? what do we call those? You can see them on the surface right there.
Well, yeah, I mean, Frank talked about that honeycomb surface. So the lighter portions of that honeycomb, that is the convection, that is the hotter portions of that plasma coming up, and then the darker honeycomb is going to be where that convection, that plasma has cooled down. As plasma cools, it gets darker. And when you get large sections of this happening, and these usually happen in pairs, not always, but usually, you get sunspots. And sunspots are these massive areas of the sun on the photosphere that are cooler portions of the surface. And finding these with a solar telescope is absolutely beautiful.
Exactly. So what I'm doing right now here, if you guys want to keep chatting for a few seconds, I'm trying to look for an image. I thought I had an image of a sunspot that I'm trying to look through here. I just realized I didn't get a chance to get that one up and running. So, but I did have some really cool sunspot imagery, but it appears that I'm not able to find it. So, but yeah, these sunspots are just absolutely amazing to look at. And the thing is that when we're looking at the photosphere of the sun, we're actually looking at the surface, and the surface is about 10,000 degrees Kelvin, and which is about, well, it varies between 6,000 to 10,000. But how can we observe the photosphere of the sun? People have asked us, how do we actually physically observe the sun without burning our eyes? And Galileo was said to be the first observer of the sun through a telescope, and he didn't use any protection. He was literally looking at the sun directly with his eyes and developed cataracts and permanent damage to his eyes. But what can we use today that can help us observe the sun's surface safely?
Well, it's a few ways, but the simplest is just to get a really good filter, right? A really dark filter to look at it through, kind of like our sunglasses, but way more powerful.
Yeah, so very, very powerful. So the question is, where can we get these filters? So people will ask us, hey, where can we get these filters? So is there a reputable source to get a filter? And the question is, what if you don't have a telescope? What if you just want to look at the sun? And actually, Justin, you want to talk a little bit about what we do at the planetarium, where we have these solar glasses, which we use for solar eclipses. But you want to talk a little about that?
Sure. The certification you want to look for is called ISO or ISO. I think there's another one called ACI. But make sure that if you do go on Amazon or you go to a reputable source and want to get a pair of glasses, and they're not expensive. There's the nice paper ones that everyone used back during the North American eclipse in 2017. There's a couple that are pretty nice. They're kind of like sunglasses, except they have the proper film. Welders goggles or welders masks are the same, similar screen that will help protect you. But you want to make sure you look for those certifications, because it's not very common anymore, but during the big hype of 2017, there were issues. And the film that you can get to go over a regular telescope is made of this same film, and you can purchase it in sheets, cut it to size for your telescope. They even make something called sinoculars, not binoculars, but sinoculars. And these are great because it gives you that extra magnification. With regular solar eclipse glasses, no magnification. You're just seeing the sun as it is in the sky as your eye looks at it. But the sinoculars will give you that 10% magnification. Generally not enough to see sunspots or prominences, things like that. That's when you really want to have a telescope ready to go. But if you do look at the sun through a telescope, you've got to be very, very careful. And, you know, Derek's been looking through the sun for years. I've been looking at the sun for years. And I usually always have someone with me because there's really very little margin for error. If for some reason, you know, you get in the habit of looking through that eyepiece all the time because you're looking at the night sky. And if for some reason you were to make that mistake, you know, your retina could be gone in seconds through a telescope. So you want to have, you know, generally someone with you. You want to make sure that you're double checking that your filter is on, making sure that, you know, that you're, take your finder scope off, because you get in the habit of using your finder scope at night. You don't want to look through that. So, but once you do, oh boy, we're going to show you some awesome pictures tonight.
So I'm going to go ahead and share my screen real quick. So Justin, you want to go ahead and
oh yeah, let me stop sharing
I'm going to go
real
ahead and
quick.
share with both of you guys, with all of you here, a couple of websites here. So we're going to go to Google Chrome, and I'm going to go to show you. This is a website called Thousand Oaks Optical. And Thousand Oaks Optical, in my opinion, makes some of the best solar filters. I've been using these solar filters for many, many years. And these are the white light filters that Justin was talking about. These are just basic standard, these super reflective coatings, filtering 99% of the light from the sun. And what you have here is you can get different types. You can get ones that are threaded camera filters. If you wanted to take photos of the sun, you get some really cool images of these sunspots. Again, Justin was talking about, you can get these silver black polymer sheets, which you can see here. They come in rolls, and you can actually design and build your own filters. And we also have, there's also ones that, you know, that actually come with your telescope. So like for this one here, so you can actually buy the filter in itself. So you can actually choose the type, size of your telescope and things like that. And it's actually really, really, and it gives you all the information about, you know, how, you know, what size your telescope is, what part you need to buy, so on and so forth. So this is a really great way to start off with imaging the sun. You can see here, again, you can see those sunspots again occurring on the photosphere of the sun, the surface of the sun, which we see here. And then here are these Sinoculars. This is Woodland Hills Camera and Telescope. This is a really great website. There's also OPT, which is Ocean Side Pacific and Telescope, I believe. Correct me if I'm wrong. You guys know. I'm drawing a blank now. OPT.
I'm drawing a blank too. I can see the logo in my head, but
Yeah.
Right.
Yeah.
But OPT Core is the name of the website. Great company as well. These are Sinoculars here. This is an 8x32 pair. This is a really good size. It's very similar to the red ones that Justin and I own for the planetarium. But these are fantastic. We actually bring these out for outreaches. And all you have to do is, you know, just use them like a normal pair of binoculars, except they have coatings on the front of the binoculars themselves. And you can actually look at the sun's, the photosphere of the sun. So these are fantastic to look at an eclipse with, or if there's a really large sunspot on the sun, you can take a look at these objects. So Sinoculars are fantastic. A white light filter for your telescope or a camera will work wonders. And of course, there are eclipse glasses that you can buy. And one of the things that you want to do, I think it's Rainbow Orchestra, right? I believe is the company that builds the solar glasses. I was like, what are they called? Solar glasses. So let me see if I can bring them up here.
And you're going to want to know all this stuff, guys, because there's an
Rainbow
event coming
Symphony.
up here
That's
soon.
what it was. Rainbow Symphony. I apologize. I knew it was like orchestra, symphony. So here we have, this is a website, Rainbow Symphony. These are the glasses that we purchased for our event. We had a major large solar eclipse event. We'll talk a lot about the solar eclipse in a little bit here. And these are ISO certified. They last a very long time. You can even get eclipse shades. I think we have this pair, right, Justin? Don't we have this pair?
Yes, they have. That's the ones we use.
So you can actually even get eclipse shades. You can even get them in different themes and all kinds of crazy things here. So you even have Eclipse viewers. This is the best way to view the sun with just your eyes. You can even get these kind of cool versions here. So lots of different options. So again, rainbowsymphony.com. This is where you can buy your solar glasses. And these are absolutely fantastic. You want to talk a little bit about some of our experiences, Justin, with our students that have seen them through those glasses?
Well, one of the things that we love to do is when the kids come out for a show, you know, they spend an hour with us inside the planetarium, and then generally the weather's pretty nice out, and we take them outside, we give them some brief instruction, and we pass out a pair to everyone, including the parents and teachers, and we take a look at the sun. And you know, it it never gets old watching these kids, whether it's 5 of them, 10 of them, or 50 of them, counting down 3, 2, 1, look at the sun, and the screams of joy and coolness factor that comes out of their mouths is just, it's indescribable. And it's amazing that even the parents, the teachers, have never seen this. So you wouldn't believe how many people. We see the sun every day, right? It's heating us up. It's giving us life here on Earth. It's amazing how few people take the time to look at it up close, even if it's with no magnification.
Yeah, absolutely. So that is kind of the beginning start of solar observing. Is, you know, get yourself a nice pair of solar glasses. Bring those with you for solar eclipses. Now, speaking of solar eclipses, where were you both during the solar eclipse? Justin, I'll start with you, and then Frank, if you want to chime in there. Where were you for this?
Oh, sure. You know what I'm going to do? I'm going to bring up the map for everyone
Great.
of the 2017. I'll
So
share
while
that.
he's doing that, if you're on Facebook right now, let us know where you were for the 2017 solar eclipse. And if you were on what we call the center line, and Justin's going to show you that in a few minutes here, or if you were here in Florida or wherever else. So Frank, what's going on with solar eclipses here? And you can see that there's this kind of dark band around the United States here in 2017, and we have another one in 2024. Can you tell us a little bit about what's going on there, why it's important for us to be on that line there?
Yeah, I mean, what we're looking at there is basically the path of the shadow of the moon across the Earth from the sun. So, you know, unless you're right underneath that shadow, which is surprisingly small compared to the Earth, right? You're not going to see a total eclipse. You know, if you're a little bit above that line or below it, you'll see a partial eclipse, which is still cool. You know, that's what I saw during the last one. And there's some cool things to observe in that as well. But if you want the full-on total eclipse experience, you got to be in that band at the right time.
You know, I had a friend of mine go up to, I think, North Georgia, and he was just at the cusp, at the border of the dark band and non, and he was at 99% eclipse. And I was telling him, you got to get 100%. You got to get 100%. If you don't, you're not going to see it. And sure enough, he missed it. He was just off, but he still got to see, you know, a majority of the sun eclipse. But still, it's very important to be on that line. So again, 2017, we see that it began in Oregon. And Justin, that's where you were. You were in Oregon for the eclipse, right?
Yes, yeah. I mean, we had been tracking this eclipse for years. You know, I think we started looking for our best spot maybe around 2011. You know, so my wife actually did something fun where she looked at this exact map. It might not have had the 2024 on it, but she was looking at the map, scanning all of our family, all of our friends across the United States of America, and going, where does our family live in this path? And oh, look at that. Uncle Mike lives right there in Salem, Oregon. Ding, ding, ding. There's the winner. So gave him a call up, and he was right in the path of totality. Now, it's amazing, even when you're in that perfect path, just by traveling a distance of maybe 30 minutes can give you just a few more seconds of totality. And so that's what we did. We were in Salem, but we traveled to a little town called Scio. that gave us an extra 10 seconds of totality. And it was the most, I was crying like a little kid. It was the most beautiful thing I'd ever seen. And what was the most amazing about it is you're watching the moon move into its place in front of the sun for, you know, I think it was a couple of hours. It felt like it anyway, waiting in anticipation. Maybe it was just about an hour. But if you didn't have your glasses on, you'd have no idea that this was happening.
Yeah.
You know, it's a new moon time of the month, of course. And so you have that, but you'd never know that the moon was making this path, this transit across the sun, even 30 seconds before totality. It was a bright sunny day. You would have had no idea that in about 10 seconds, you know, the temperature was going to drop 20 degrees, the crickets were going to start chirping, birds would stop singing, and then you see this image that we're going to show you here, and I'm sure you've all seen eclipse pictures, but we've got some that Derek's taken in detail, and it's incredible.
I have something better, Justin, if you want to share that, and we'll look at my pictures too. But where I was in the Sawtooth Mountains in Idaho with my wife Lisa and my friends Mark and Michelle. So we found a campsite in the middle of nowhere in the Sawtooth Mountains in Idaho. It was incredible. What I'm going to do now is I'm going to show you all a fisheye image of the eclipse that I took. Now, hopefully the sound works. So let me know, Frank, Justin, let me know if the sound works with the video. So we're going to go ahead and take a look at this video here.
You have sound.
So here we are at the campsite in the Sawtooth Mountains, and you'll be able to hear the reaction and the experience of what we experienced. We actually use this in the planetarium dome to simulate what it's like during an eclipse.
Love the screams.
You can hear me go, wow. Now that little bright dot you see there, that I believe was Venus, was it not? I think Venus was visible that day.
I think you're right.
Yeah, that is Venus, yeah.
Chime in, audience, if you remember.
So as you can see, darkness. It was truly an amazing experience. If you haven't seen an eclipse, I super recommend that you do.
Well, if they haven't, when's their next opportunity here, Derek?
Well, we're going to talk about that when the eclipse is done. We're going to feel like we're actually there right now.
So this is all real time, right?
It's all real time. This is a real video. Yeah, this is
excellent.
So just to give everybody an idea of how fast this eclipse lasted. You know, when I look back at this video, I realized it actually went pretty long, but man, it lasted literally, it felt like it was only like 10 seconds. And I think we're almost to the end of the eclipse. Oh, they were taking some photos, getting some. By the way, it was 23 degrees outside at this time. I'm wearing no jacket because I'm just in pure adrenaline. And then it just, yeah, there it goes.
That was in August too, right? I mean,
it was in August, but I was also 8,000 feet above sea level. So and you can see there's Lisa right there in her puffer jacket. And I was an idiot wearing just a shirt in 23-degree weather.
Wow.
But anyway, so yeah, so Justin, can you bring that that image of the map of the eclipse up again? While we're doing that, just
Oh yeah.
so where were you? I apologize if you said earlier. Where were you for the eclipse?
I was in my backyard, and we only had a partial eclipse here, but it was still pretty cool. One thing that we saw, like you said, like you would never know it was coming. Like unless you have a total eclipse, your eyes adapt to it. The sun is still really bright even when it's obscured, and unless you're actually looking at it and observing it through those filters, it's kind of hard to know what's going on. And we did have those filters on binoculars that we used to observe it with me and my family, and it was cool to see it almost go total, but we didn't get the full experience. We did see those really cool shadows, though, and I actually have a picture of that here if you want to take a quick look.
Yeah, yeah.
Oh yeah.
Yeah, let me share my screen real quick. And I won't pretend to like totally understand the optics and physics behind this, but this is actually the shadows coming through the leaves of a palm tree in my backyard. And if you look closely, like you can see lots of little crescents there, and that's actually the crescent of the sun, what's not obscured by the moon there, shining through, sort of like a pinhole camera effect, I think is how it works, right? Through the
Right.
holes between the leaves. And that was a cool thing to see.
Yeah, it's truly remarkable to be able to see something like that. And could you imagine I could imagine why ancient civilizations thought these things were just, just one day
Bad omen, right?
it
Yeah.
just disappears. All right, so Frank, your job now is on April 8th, 2024. You're going to have to pick a location. We got another total solar eclipse happening. And this one's actually almost double the length. I think it's like 4 minutes for the totality. So the last one was like 2 minutes and like 26 seconds for the maximum extent of the eclipse. But this one is double that.
Wow.
Over 4 minutes long. So this will be incredible. And it enters in through the western side of Mexico and heads up into the Rio Grande, and eventually enters Texas through Arkansas and Missouri, Illinois, Indiana, Ohio, a little bit of Pennsylvania, a little bit of Canada, and New York, and up into Quebec and Vermont and Maine, and a little bit of New Hampshire, and all the way up towards Labrador. So as you can see here, you got to pick your place. And I'm right now looking for Arkansas. And the reason for that is because I'm a rock hound too. So if I can mix eclipse with looking for quartz crystals and potentially diamonds at the Crater of Diamond State Park, I'm going to do it. Justin, where do you think you're going to end up being?
Well, this one's tough because I've got family in Buffalo. My father lives in Indianapolis. I've got an aunt that lives in Dallas. I think for me, I'm going to spend the next 4 years trying to get an idea of what the weather is actually going to be like in April in each one of these places. I feel so bad for people that traveled, got in planes, got rented RVs and traveled to places. Now, that could happen no matter what, of course, but what are my best odds for the best weather? So I'm thinking somewhere further south. As much as I'd love to be in Buffalo or Indianapolis, I've heard the weather that time of year is pretty tough. So I've got to go probably where the weather's best.
How about you, Frank? Do you have any ideas?
Well, I live in Florida for a reason because I don't like being cold. So, I'm going to offer someplace south and someplace with a lot of open space. So southern Texas is looking pretty appealing to me right now. But
yeah, I mean that would be pretty awesome too, right over there in that kind of Rio Grande area. That would be pretty nice.
Yeah. But if we're patient, right? I think there's another one. Like if you're really patient, there's one later on that actually goes right over Orlando, isn't there?
2040.
I forget what year it is.
Yeah,
Let me
2045.
pull that up.
I always make the joke that that's going to be my retirement day.
Yes.
Because how can you compete with that, right?
What a way to go out.
Outreach event is right over Orlando, Central Florida. Yeah.
Oh.
It's not even so cool that it's going over Florida, but totality is over 6 minutes.
Wow.
I mean, Oregon was I think 90 seconds, which was a blink of an eye. I didn't even want to take a photo. I just wanted to enjoy it with my eyes. But 6 minutes, I mean, wow.
Not only that, but I'm looking where the 6 minute line is. That's right over Disney World. Can you imagine Disney World on that date?
Wow. Do we know what time it is during the day? Or
get your tickets now?
I don't remember what it was either. But
It's got UTC there.
Well, that's universal. So that would be it would be in the if it's 5
Please
hours.
not 4 o'clock.
What's that?
Please not 4 o'clock when we have
No,
our
no.
afternoon
That is
thunderstorm.
that's 5:30. So it would be it would be a morning actually. If
Even
it's
better.
universal
Wow.
time, yeah, it'd be 5 hours difference. So yeah, so there you
that'd
go.
be pretty trippy.
That'd be pretty awesome, and that'd be perfect. I don't. It was in August. August, right? Wasn't the date was August?
Yes, I believe so.
Yeah. So
I
definitely
believe so.
morning would be really good here in Florida. So, with our luck, there'll be a hurricane going right.
That is likely.
You know, hurricane ruins the eclipse. You know, with our luck, because August.
2045. So put that date on your calendar and be ready and get your glasses now, right? I know stuff. Derek, some of the glasses, though, I've gotten a lot of comments about the film expiring. Do you know any more details about that? I don't want people to buy them now. And then...
The Rainbow Symphony glasses, if you keep them in good shape, they should last for a very, very long time. I don't know until 2045, but they'll last you for till the 2024 eclipse. That's why I always recommend Rainbow Symphony. They're the best, in my opinion, out of all the different solar glasses. But if you get, welder's glass, you can do W14 welder's glass. But also the solar shades, they're built to last. So do yourself a favor and get yourself a little bit higher quality solar glass, because if you're observing the sun, you could see, so.
And just don't wait. I mean, it was a madhouse with those glasses.
Right.
They were like the hottest item on Earth for 6 months leading up to it, and they ran out.
Yeah, you thought toilet paper was bad.
Well, we actually did a solar. We had like 5,000 solar eclipse glasses, and we had an open house, and it was like Black Friday. I mean, it was just bonkers. But the sad part of the sad reality is right after the eclipse, I saw people just chucking the glasses on the floor. It was like,
don't tell me that.
How quick it goes from being a hot commodity to just people. And I'm like, what are you doing? You can use these glasses to observe the sun. And I don't know. So, all right. I have a couple of photos from the eclipse that I'll share with all of you here. So I'm going to go ahead and share my, all right, let me go ahead and share my desktop here. I believe I have to do that. So right here, this is an image of what we call the chromosphere of the sun. And we're actually going to talk about that in a little bit here. We have another type of telescope system that we use called a hydrogen alpha telescope. And this allows you to look at the chromosphere, which is a layer just above the photosphere. And the reason why it's called chromosphere is it has this red color. It's because of the hydrogen. And you can actually see these large prominences. Look at this giant thing. We're going to talk about prominences later on as well. But these are these big puffs of gas, big, clouds of gas, hot plasma that's streaming off of the sun. It was an incredible fact that we could actually see that during the eclipse. I think that was just absolutely brilliant. Now, one of the interesting effects that happens during an eclipse is because the moon is not smooth, since the moon technically has craters, when the moon is going in front of the sun, what happens is, let me zoom in here and take a look. What happens is that you can actually see a little bit of the craters. And what happens is a little bit of that light from the sun peeks out. We call these Bailey's beads. And so what happens during this time is you get these little glimpses of light that peek out from the craters of the moon. I think it's just absolutely amazing that we can show that, it's not smooth, it's rigid. But of course, the moon eventually completely covers the sun. And we get, of course, this. And this is a HDR composite. What I did here, and actually I kind of cheated. I used a program called Eclipse Maestro, which is a Mac program. And what it does is I hook up my camera, and it will literally, if I know my GPS coordinates, it will sync up my camera and will actually get the camera settings exactly when and where and how to get this image. So that allowed me to really spend time enjoying the eclipse. Of course, I was still worried to make sure that it was going on, but it worked perfectly. So I was able to get shots of the corona. I was able to get the chromosphere. I was able to get the actual I overexposed, so I can actually get the what we call earth shine, which is light reflected back towards the moon of the earth. You can actually see there the Maria on the moon, so you can see the moons there. I mean, this was a shot I wanted, and I remember I submitted this to APOD literally like an hour after, and it got selected as the astronomy picture of the day for the next day. And I remember I was driving and I got a notification, and I felt like I was Kevin Bacon in the Apollo 13.
Well, you just got to imagine how many thousands of images they received from the public, and to be able to get yours selected that's quite an honor.
And I'm not going to lie, I felt really bad at the time. We had an event at the college, but I knew that I had to be there for the eclipse. And sure enough, because we were selected, the M.O. Buehler Planetarium at Seminole State College got national recognition, international recognition for this. So not only did we have this amazing event at the college that Mike McConville, who was working with me at the time, put on this fantastic event, and he has such a high praise on that. He'd done a great job with it. We also got a chance to feature an actual shot of the eclipse, which is now recognized nationally and internationally. So it was a great day for us, and it was a lot of work, a lot of planning, a lot of stress, but in the end of the day, it worked out really well. So here's an image of the entire eclipse. So we have the beginning here. We can start seeing the moon start to go and continue and continue. And of course, Frank, you probably saw something akin to this, right?
Right around there.
Kind of a crescent sun there. And then the first event is what we call the diamond ring. Essentially what happens is you get this kind of very thin light of the sun, and you get this really bright side of the sunlight, and you get this kind of it looks like a ring. And then of course we have totality, and then I took some images of the Bailey's beads and other things like that, and of course we can see the opposite effect. Now, what's really interesting, I don't know if you experienced this, Justin, but because I was photographing the entire eclipse, once totality happened, everybody just left, I felt like. I don't know if you had that same. Me and my buddy Mark and my wife and his wife, we pretty much were the only people still around taking photos, and everybody else kind of.
They bolted, huh? Yeah, we were in a pretty remote area, and so there weren't too many people around us. But I remember my cousin driving out from Seattle, and he spent, I don't know, hours in the car with his daughter racing to get there, and he literally got there 5 minutes before totality just to catch it, and just caught it just in time. And then we stayed and watched the rest of the moon moving away, and then back to a regular day. So we took it every second in that we could. I think one of the coolest things about an eclipse too is that, I think most people probably know this though, but an eclipse is what helped prove Einstein's general relativity. Sir Arthur Eddington in 1919, astronomers were going out. Einstein wrote this amazing proof, but he had really no way to prove it, right? He did the math, he wrote everything down, everything looked good, it made sense, but without being able to prove it, how do you prove, these calculations? And using an eclipse, we were able to prove that this fabric of space can be bent, and light can bend, and astronomers were able to see stars that you shouldn't be able to see because the mass of the sun is bending space and time. And I think that is just one of the coolest things. Eclipses themselves are amazing, right? But just knowing the history of this is fantastic.
And of course, the Mercury transit also helped with special relativity as well. So by studying the sun and the different events that happen with the sun, like we call transits, basically objects passing in front of the sun, we are able to figure out some really cool science. So now, speaking of science, Justin, you are a space exploration guru. aren't there some missions that are currently, studying the sun, or
Yeah,
going to be studying the sun?
we've got a couple. Geez, okay, so we got to go back to 2018, August 12th, 2018, the Parker Solar Probe. This was a pretty large spacecraft. It was so big that it went up on a Delta Heavy rocket. Derek, do you have your shirt on? I got mine on.
I do, yes, I do. But I'm sharing the launch
through.
photo right here.
Oh, good. That's all right. Well, yeah. So this Parker Solar Probe it's actually named after Eugene Parker, who's a famous solar astronomer. And the coolest thing about this was this spacecraft. You know, NASA doesn't usually name spacecraft after living scientists. They're usually, passed away by the time they name a spacecraft after it. And they named it after Eugene Parker, while he was still alive. And he was there at the launch watching this spacecraft take off. And he's still alive now. I think he's around 92. There's some amazing science coming up, and knock on wood, he's around to see some of that. But this rocket went up in 2018. It's going to take about 7 years to get to the sun, and that's kind of the irony about traveling to the sun. The sun is actually one of the most difficult places in the solar system, if not the most difficult place in the solar system to get to. We're only 93 million miles away from the sun. It takes the same amount of time to get to the sun as it takes to get to almost to Saturn, which is almost 1 billion miles away. Because you've got, Earth is traveling around the sun at something like 30 kilometers per second, and you actually have to shed velocity to get to the inner solar system. And so this spacecraft is on its way there now. It is currently the fastest spacecraft that's we've ever built. And by the time it gets to its closest approach to the sun, which is going to be about 5 million kilometers, which, put that in perspective, Mercury is about 28 million miles from the sun. Parker Solar Probe will reach 5 million kilometers from the sun. So really, really close. And its goal is to really study the structure, the dynamics of the sun, the coronal plasma, the magnetic field. You've got these crazy solar winds coming off the sun, which Derek's going to talk a little bit about that a little bit more. And these can be pretty damaging to Earth. I mean, geomagnetic storms are nothing to mess around with. There was one in 1859 that knocked out, power lines, phones, was giving electrical shocks to telegraph operators. So these are things that we need to learn and understand how they work. But one of the coolest things it's going to study is that the corona, the atmosphere of the sun, is 1 million degrees compared to the surface of 10 to 12,000 degrees. Why is that? What are the details there? But the coolest thing about Parker, I think, is going to be that it has these imaging cameras on it that are going to give us still and video of the corona, the solar wind, solar ejecta. So I cannot wait for 2024. We have an eclipse, and Parker Solar Probe is going to start bringing us back this amazing science.
Lots to look forward to, that's for sure. And of course, we also have another mission to the sun right now. Of course, is the solar orbiter.
Yes, this was earlier this year, and we just made this launch before everything got crazy with the wrath of 2020. But the Solar Orbiter is a European Space Agency spacecraft, and they kind of collaborated with NASA, but it's essentially built by ESA, and it launched February? It was early February, and it didn't go up on a heavy. It went up on a Atlas V. It's still a beautiful night launch, another sun observing satellite. And this spacecraft is going to really be trying to study the kind of the inner heliosphere of the sun. The heliosphere is that entire area of the corona that is goes pretty much from where the sun is out to the Kuiper belt. And so it's going to be studying that inner heliosphere, studying the solar wind. But the coolest thing about the solar orbiter is it's basically going to bring us the first ever images of the north and south poles of the sun. The way it will orbit will be pitched in such a way that its cameras will give us the first ever images of the north and south poles of the sun. So this is going to be just incredibly cool. And I saw something, I think it was today, I shared it with Cephas about the solar orbiter is going to pass through, we were looking at Comet Atlas earlier this year, it's going to pass through the dust tail, I think, is it tonight or tomorrow?
I think, yeah, sometime within the next 24 hours.
And tell us about this picture that you took. I mean, this is the solar orbiter taking off.
I know. That's the top of the VAB, isn't it?
Yes. Let me reshare. I realized
Let's talk about that photo, man. That's awesome.
This is the roof of the vehicle assembly building, the structure that assembles all the massive rockets, like the Saturn V and the space shuttle, and eventually the Space Launch System. And I had a chance to actually take this photo of this launch from the roof of the vehicle assembly building. So, it's truly remarkable that, it was just, there's no word to describe it. And know that this rocket is heading to explore the sun is truly cool. Now, what I really find interesting about the heliosphere is I want you guys' opinion about this. So by definition, some astronomers think that the solar system is defined by things in the heliosphere of the sun, the influence of the sun's heliosphere. However, we know that there are chunks of ice in what we call this hypothetical Oort cloud that extend almost a light year away from the sun, that are being held by the sun's gravity. So what do you define? So this is actually a debate right now, is how do you define our solar system? Is it anything influenced by the sun's heliosphere, or is it this Oort cloud? And what do you guys think? What's your opinion about it?
I mean, I'm on the gravity side myself, I mean, gravity is sort of the universal glue that holds the cosmos together, and it's the fabric of the cosmos itself. So personally, I think we were focusing on the heliosphere and the heliopause just so we can say that Voyager left the solar system more than anything else.
This is true. Yeah, that was a thing. That was about 15 billion miles. Essentially, the Voyager spacecraft was able to detect the interstellar medium, basically, away from this heliosphere. But yeah, I mean, there's still stuff out there. I mean, it's just because the heliosphere's density is nothing at that point. There's a term called heliopause, where essentially the heliosphere basically just kind of stops. But at the same time, yeah, I mean, there are things out there that are not being influenced. Well, Justin, what do you think about it? Are you in agreement, or do you think it's the other way around?
I mean, if the conversation is related to maybe the possibility of life, then I could see where the heliosphere might be a factor. But I agree, with Frank, that gravity to me always wins. What is being held in gravity, what is being affected by that is got to be the kind of key indicator for me. And, I just want to finish with Pluto as a planet.
I wanted to ask about the space engine there, because it had a bunch of scientific information about the star on the left there, and it said we have 13 planets. What's up with that?
Oh yeah, go. You take it, Derek? You want to take that one?
But the space engine, is that what it said in there?
Yeah.
That we have 13 planets.
Well,
we can tell you why.
I mean, from a planetary scientist point of view, planet is an object that orbits around a star, right? And I think our definition of planet has evolved over the years, and technically we have 8 major planets and 5 dwarf planets, and that makes 13, right? But here's the thing, though. Sedna and QR and these little guys, they didn't get credit. They didn't get credit, but yeah, I mean, technically our Earth is by definition a terrestrial planet or a rocky planet. Uranus is an ice giant. Jupiter is a gas giant. maybe Pluto is a dwarf planet, and we're starting to kind of become more open on our definitions of what a planet is. So I think, and I guess with Space Engine, I guess they decided to say, well, there are technically 13 planets, 8 major planets and 5 dwarf planets. There's your 13, right? So.
Well, Pluto's happy then.
So Pluto's happy. There you go, right? And here's the thing, maybe we could do a whole episode on all of that. Maybe we can get a couple of people else in there, and we can start having good discussion about Pluto. What's the deal?
Oh yeah, and Douglas in the chat, he brought up, Planet 9 is out there, and he's right. I mean,
right.
Another thing. Everyone sometimes asks about, what are the coolest things about each planet, and if you ask me about Neptune, the coolest thing about Neptune is it was discovered using mathematics. Those same mathematics tell us that there is other objects in our outer solar system that are affecting the orbits and the gravity of these Kuiper Belt objects, these outer planets. So the math tells us, just like the math told that when they did the math, they said, astronomers, point your telescope over there in the sky, because the math tells us that there should be a planet there. And sure enough, that's how they discovered Neptune. So it's just a matter of time before we find more in our solar system. We have not discovered everything.
And to say that we've made our final decision on what is in our solar system is kind of premature. I think we are learning so much more about our solar system, and it's going to be. I think the next 50 years are going to be, next 100 years. Next 50 years, because I like to be realistic with my age here. They're going to be incredible. So before we continue on, Justin, do we have any questions or anything from the Facebook page?
Not a lot of questions, but a lot of cool comments about where they were. People were all over the country during the eclipse. A lot of conversation about the glasses and things like that they've used. We had a lot of CFAS members, Central Florida Astronomical Society members, tuned in watching the show. So thank you for that. But no, let's get to these recent images you took this week.
So while I get these images up, Frank, you're the telescope man. How about you tell us a little bit about the type of telescope that I was using? This was a Lunt 60. This is a hydrogen alpha telescope. Do you want to talk about the different other types of telescopes one can use to observe the sun besides white light filters?
Yeah, I don't have a solar telescope myself, so it's not really my area of expertise, but, you can also get these hydrogen alpha filters as well, right? That let through a very narrow wavelength of sun. And basically, the more narrow that wavelength is that you're looking at, the more detail you're going to see on the sun's surface. So, you can get these hydrogen alpha telescopes out there that are specialized. Or if you just want to start simple, you can slap a filter on the top of a normal telescope like we talked about before, but you're not going to get that kind of detail that you're going to see in the photos that we're about to see now.
Yeah, this particular image is what Derek was using this week. We were actually at a charity golf tournament that we are part of each year, and we sponsor one of the holes at the tournament. And we love to show people the sun during, before they hit their balls for the tournament. And so we have the Lunt is the name of the company that builds these telescopes. What you're looking at here is a scientific telescope specifically designed for solar viewing. So it doesn't have a solar filter on it. It is a solar telescope. And you can see the red camera there on the eyepiece. That is there to capture the images that Derek's about to show you. And we've got it tracking the sun throughout the day, and boy, we were in for a treat. We saw some wait till you guys see these pictures.
So and we were trying to maintain our social distancing. We were invited to this event, and we didn't want people looking into the telescope. So Justin brought his TV down there. I hooked up the camera, and bing bada boom, we got this. So what I'm going to do here is I'm going to go ahead and go to this. I have it on another computer here. These files that we actually collect, this one in particular is 10 gigabytes in size. It's uncompressed. And what I'll do later on is I'll show you the final image, and Frank can talk a little bit about the process there while I get the image. But let me show you all the video here. So this is, let me go ahead and start from the beginning. So what I did with this image here is I overexposed the sun, and the hydrogen alpha filter looks at an area of the sun called the chromosphere, which again, we talked about that earlier. It's this layer above the photosphere. And this is a monochromatic camera, so it's taking an image in black and white. So so that's why we only see black and white here. But if you look over here, you can see this just massive plume of gas shooting off of the sun, and you can actually see the clouds rolling in. This was a cool image. I like this because it kind of shows you, we have to fight with this stuff here. But there's another image of this prominence here. Again, these large plumes of gas are caused by magnetic fields, the same magnetic fields that are twisting down into the convection cells of the sun are twisting upwards, and the plasma gets kind of pulled up into these magnetic field lines and essentially generate these large plumes of gas. Now, we don't really have the exact estimation, but you could fit the Earth inside here, this gap here. And so essentially what happens is these magnetic fields pull the material up or around in these what we call loop prominences. You can actually see one forming right here. Two magnetic fields are combining, reconnecting, and they're moving that material up above the surface of the sun. And so you can see in these two images here, we have this thing is just absolutely massive. Now, eventually, though, in these magnetic fields, sometimes they can snap apart. And what will happen is you will get basically these plumes of gas that get suspended into the chromosphere of the sun. But sometimes these magnetic fields will snap to the point where it will thrust a tremendous amount of material out from the sun. We call it a coronal mass ejection. And sometimes these coronal mass ejections can be very, very, very powerful. Justin was talking about one that happened back in the mid-1800s. Where a telegraph company had all these power outages. And what's interesting is that I think there was one company that actually was able to use their telegraphs because of the amount of electrical force that actually was produced from this event. And this you can't really see this with a white light filter. You have to see it using a hydrogen alpha filter, because you're looking at one particular wavelength of light, when what we call hydrogen alpha, and that's what we primarily see in the chromosphere is hydrogen alpha. So that's what we're seeing here with these images. And what I'm going to do now is I'm going to go ahead and search for the image. We actually can underexpose and actually look at the chromosphere in a different light here. So let me go ahead and look up that video. If you guys want to chat a little bit more about kind of prominences and what, maybe something about, maybe you all would be interested in sharing space weather. Maybe Frank, you want to talk about space weather and spaceweather.com, and we can actually see the effects of the sun here on Earth.
Yeah, I mean, I think we're actually like entering sort of a more active period of the sun right now too, aren't we, Justin? We've been sort of a solar minimum.
You've got a solar minimum, solar maximum, and it's about an 11-year, on average, 11-year cycle where you can see a lot of solar activity happening, sunspots, solar prominences, coronal mass ejections. And this is important for us to understand. This is in 2012. That was when the world was supposed to end, right? Was that the Mayan year?
Yeah, they were off by 8 years, but close enough.
Oh, good point. There was a coronal mass ejection that was so large that if it had hit Earth, the damage that would have caused to our electrical grid, to our satellites, they said would have been just beyond catastrophic, that the power would probably still be out. So, the nice part about Earth being as small as it is, orbiting around this massive star, is that, the timing's got to be just right for us to be affected by one of these. But it is absolutely critical for us as a species to know, understand more about how these work, how to get more notification. And the solar minimum, like you said, is this an 11-year average period where you have lots of activity and minimal activity. And we're trying to understand that more. And we're coming
Yeah.
into a point now where we're starting to see some changes, which is pretty exciting.
Yeah, and if you want to monitor those changes, just head over to spaceweather.com here, and you can actually keep tabs on it. So you can see here they're talking about solar cycle 25 starting up, and there's a specific sunspot we're looking at. It's been a while since we've seen a sunspot, guys. So, this is pretty exciting for people that want to observe the sun and see interesting things. But, it's also at the same time concerning because it can interfere with our satellites and some of the technology that we have here on Earth. So
we just
Yeah, on the
clear night,
yeah.
clear day. That's all we need.
On the ISS, on the International Space Station, there are 2 Soyuz that just kind of stay docked on the ISS at all times. They're lifeboats. They're literally lifeboats that if a CME is heading towards Earth, they have time, because it takes light photons from the sun, 8 minutes to leave the sun and get to Earth. But a coronal mass ejection can take anywhere between 15, 17 hours. So they have these Soyuz lifeboats on the ISS that the astronauts can quickly get off the space station in an emergency, which is crazy. But yeah, we got a lot to learn about our star.
And that's a good question you bring up, Justin, is when we want to go into deep space, we want to head to Mars, we have to consider that we could be bombarded by a massive solar wind effect or coronal mass ejection, and that's something that by studying at the ISS and beyond, we can get a better understanding of how we're doing that, because as we get further and further away, we don't have the protection of the Earth's magnetic field, and even when we went to the moon, we had effects from the sun, didn't we?
Yeah, I mean, it is definitely something that needs to be. I mean, Mars is going, we imagine this world where we're walking around on Mars and we're farming and everything's hunky-dory. That is not the way it's going to work. Our Earth has this fantastic magnetic field that is protecting us from solar radiation that can damage the cells in our bodies in such a way that Mars does not have those protections, and there is no way that we could live for any long period of time at the surface. We would have to be underground, shielded, and this is a big concern for astronauts traveling 9 months to Mars. Is their protection of our cells and our bodies from solar radiation.
And that's a scary thing to think about, how fragile the human body is. And you think, Frank, I'm sorry, my friend, but it's not going to be like Star Trek going on a spaceship to Mars. It's going to require a lot more work. Now, of course, in Star Trek, they had all this fancy schmancy technology that helped protect them and all that. But at the same time, we have to be considerate of the fact that the sun is this big, giant, hot ball of plasma that's spewing out these massive amounts of particles. And actually, the MAVEN spacecraft that's currently traveling around, orbiting around Mars, has discovered that those solar winds have actually stripped atoms in the Martian atmosphere. And think of it like a sandpaper. It actually stripped it away, slowly deteriorated, because of the fact that Mars lacks an magnetic field. And because of that lack of magnetic field that normally would protect Earth, Mars didn't have it. So over time, that withered away the atmosphere. And kind of an interesting thing, Frank, you posted just not too long ago on your own personal Facebook, but there was this article that you posted about the Earth's magnetic field. You want to talk about that?
Yeah, I mean, if you want something new to worry about this year, it turns out that it actually turns out that over the past 200 years, Earth's magnetic field has reduced by 10%, believe it or not. And that is crazy. It's probably nothing to worry about, because they think it just has to do with like this subduction of oceanic crust down around South America somewhere. So it's kind of like blocking the magnetic field in that area. Probably a natural geological thing, but still 10% over 200 years, that's a little concerning, because we do need that magnetic field to protect us from that solar radiation. And without that protection, we get fried, and that's not good.
So as much as you think the sun is good for us, the sun is given life on Earth. I mean, without the sun, we wouldn't be here. But at the same time, the sun can take it away, right? And we need to be considerate of that as well. So what I'm going to do now is I want to show you all another image of the sun that I've taken during the time when we were out at the event. And this is so I reduced the exposure in this one, and this right here is a view of the chromosphere. Here we go. The chromosphere from the view of the and what we would see with our eyes. This is essentially what our eyes would see. The prominences would be a little brighter, but you can see that churning, bubbling effect that lingers above the sun's photosphere. And all that material is just moving and twirling and swirling around. And if we were to actually do a time lapse of this, we would be able to see this motion. So, the sun is not, again, this light. It's this churning, dynamic, evolving ball of hot plasma that's constantly changing. And what I love about observing the sun is that, and Justin, when me and Justin were watching it, we were seeing things change. We were seeing that prominence slowly change shape and new ones coming up and all this stuff. And what we get is, we get to see our sun in a very interesting way. Now, I don't know if you just saw it. Did you guys see that? Did you see that little, it almost looked like a satellite or something. I might have to go through my frames here, and I'm clicking on the wrong, there we go. Let me see if I can see that. Did you see that? Yeah, I'll have to look and see. Maybe I captured a satellite or something. I don't know.
Or it could be the transit of a bug.
Or it could be a transit. What I'm going to do, though, is I'm looking at those frames, and I'm going to look at them more in depth. But anyways. All right. So one of the things that what you could do with these movies, is you can stack them and create a final image. And Frank, do you want to talk about the process we use for when we do planetary imaging, whether it be the sun, the moon, or the planets?
Yeah, it's all the same technique. So, in all of these cases, we're looking at a relatively small object. Well, the sun and moon are pretty big, but, you're still fighting with the atmosphere. That's your enemy when you're trying to take really detailed photos of these objects, where you're trying to capture these, specific geological details, or, prominences on the sun, or, convection cells, or what have you. Your enemy is the atmosphere and the turbulence in it, because that's going to make your image wavy and indistinct. So what we do is called lucky imaging. And the idea there is that we take a very fast video, like you were just looking at, and we have software that can analyze that video and pick out the very best frames where the atmosphere was the most still and we have the clearest images. Then we can select those frames and do what we call stacking to average those best frames all together and sort of get the best information from the very best frames that we have from that video. And when we're done, we combine that into what is hopefully a really awesome image.
And so what happened here is, now here's the coolest part too, is that since we're actually looking in the hydrogen alpha wavelength, I was able to create a false color image to kind of create a little bit of a view here. But this is the final image taken of several minutes of exposure. And this really gives you a feeling of seeing that prominence, forming and growing, and you can see the magnetic fields twisting around and the materials distorting. But the other thing you can see are these specules, and the specules are actually these almost like fountains of plasma that get shot up above the atmosphere, or above the photosphere of the sun. And some of these can be 1,000, 10,000 miles across. These ones are probably only a few thousand miles across. This prominence here is most likely between probably 25 to 30,000 miles across. And again, you could fit the Earth is about the size of this crosshair here. So again, giving you an idea of the size, but you can see all these that's another specule there. You can see that's a larger one that's formed. Again, that's about the size of Earth right there, just to give you an idea there. And you got these other prominences that are coming off of the sun there. But again, you can see the granulization, the churningness of the sun. It's just remarkable to be able to capture this and capture it from here on Earth in a small telescope. So a hydrogen alpha telescope is a telescope that would be, if you're really a serious solar observer, this is the one you want to get. But, you want to start out with a white light filter first. This will give you a view of the photosphere. You can see sunspots with it. But if you're really down and dirty, getting a hydrogen alpha scope, but there's other ones too, aren't there, Frank? Aren't there other telescopes that we can use besides hydrogen alpha? There's things like calcium, right? There's some other types of telescopes we can use.
Yeah, that's right. I remember on a trip out to, I think it was the Lowell Observatory, they had a calcium telescope out there on display as well. So yeah, there's different wavelengths you can look at, different emission bands that you can observe in the sun, and they all have their own character, right?
And why are we looking at calcium?
I would have to ask you that question, Derek. I'm not a solar guy.
Well, so our sun is actually not a purebred star. Our sun.
Oh yeah.
Our sun is a second generation star. So the oldest stars in our universe were pretty much pure hydrogen. But remember, those big, bright, hot stars fuse really heavy elements in their cores. And when they exploded as supernovas, when our sun formed, it had some stuff in it, other elements. And so we can actually observe those elements in the sun as well. So,
yeah. But why calcium, Derek? I mean, I would think that, carbon would be there before calcium or something, right? Or oxygen. So what's special about calcium?
That part is still, I don't know much about the process, the engineering behind why calcium comparatively. If you know the answer to that, if you're in the comments, let us know. We love to hear it.
I'm curious now.
But I don't know why calcium is the one that's chosen comparatively to others. Justin, do you have any information on that?
Well, since we're talking about elements of stars, can you explain to our audience, what are we looking at here?
That is pretty much how we view it. Actually, my friend who's a chemistry professor at the college, she gives me crap about the fact that astronomers call everything else metals instead of hydrogen and helium, and there's iron. That's it. But everything else is either metals or gases and like hydrogen and all that. But yeah, I mean, essentially, the supernova poop essentially is what is released from these supermassive supernovas that are fusing these really heavy atoms in their cores. So in reality, I mean, if you think about it, we are all star stuff, right? We talked about that in another previous episode, didn't we? That we're all star stuff. We are the builders. We're built from dead stars, which is kind of a weird way to think about it, right? And our sun, and that's actually, why don't we talk about the sun? We get this question a lot, right, Justin? Especially when we have kids visiting the planetarium, and they ask, what is going to happen to the sun? Well, Justin, you have Space Engine. Do you want to take us to a Planetary Nebula?
Oh, sure.
You choose. Maybe the Ring Nebula. Maybe maybe eventually we'll be able to look at the Ring Nebula in one of our virtual star parties if we ever get clear weather again. But
this is a good parable of iron.
Our sun doesn't have enough mass to fuse these really super heavy elements. It's going to fuse hydrogen, helium, and helium into carbon. And eventually what's going to happen is as the core becomes mostly carbon, it's going to eventually collapse. And the outer layers of that star are essentially going to just wither away like an onion, going to peel away. What happens is the core collapses, creates these shock waves that basically push the material out from the outer part of the star. And you get these basically ring effects, if you will. And you get what's called a planetary nebula, because when they observed these, the astronomers saw them as kind of these, they look like planets because they're really small and very in small telescopes there. This one is a famous one that's visible in the summer sky. This is called the Ring Nebula. And essentially, a star about the size of our sun has died, and the outer layers of that star have essentially withered out. They have basically, the material from that star has expanded out into space, And what's left over in the star is essentially a burning hot ember of carbon. And that carbon core, which we call a white dwarf, is going to burn for several million years. And that's pretty much the fate of our sun. Our sun is going to form into a planetary nebula like this. But before this happens, as our sun begins to fuse heavier elements in its core, the sun is going to get fatter. The expansive forces that are pushing out from this explosion happening in the core is going to push and bloat the sun, and it's going to get bigger and bigger and bigger and bigger, and it's going to actually get to the point where, believe it or not, our Earth is going to be consumed by the sun. Now, before you start freaking out and going to buy toilet paper, this is not going to happen for over 1 billion plus years. So we got plenty of time. But here's an interesting fact. Our sun is going to get bigger, and it's going to get warmer here because the distance between the Earth and the sun is going to decrease. And what's going to happen is our planet is going to warm. And we think that we have about 500 million years of time before looks like we're looking at Zoom. There we go.
About that.
That was weird. Like a meta thing. We're looking within. About 500 million years is how long it will be until our planet will become so hot that the oceans will evaporate, that the solar wind from the sun will vaporize our atmosphere, or not completely our atmosphere, but what's going to happen is it's going to make it just too hot to sustain life on Earth. This is the Eskimo Nebula. This is another. If you want to bring up the exposure a little bit more, Justin, that will help us see it a little better. There we go. Perfect. Yeah, that is fantastic. This is another planetary nebula. And
so they're looking at a dead star here, right?
Essentially looking at a star,
about the ghost of a star
that has died. So when we look at these objects out in space, we're looking at kind of a time, we're traveling in time almost, kind of seeing the fate of our sun.
And the diameter of this is over a light year.
That's right. So just imagine we talked about earlier, the Oort cloud of our solar system is about a light year. And so essentially this is kind of what our solar system will look like in about a couple of billion years from now. So again, that star has collapsed. Its outer layers have expanded out into the solar system, and that hot ball of carbon called a white dwarf is exciting all of that gas that was inside that star and causing it to fluoresce, and that's what's giving off that color. So the different colors tell the different types of stuff in there, different types of elements. So really interesting stuff. Our sun. This is the fate of our sun. And, we have a while before we really have to worry about this, but this is to kind of give you a glimpse of the future. And, oh, wow, now this is really pretty.
Look at that.
Yeah.
I think this is the first time I pulled this one up in Space Engine.
Yeah, this is really, really pretty. And, again, some of these planetary nebulas can form some really interesting formations as they expand out, and that's just because of the way that the star has collapsed, and the shock waves and different other elements found in the star have basically pushed out from that white dwarf. So again, don't freak out. We don't have to worry about the sun going off anytime soon, but it gives you a better appreciation of the fact that our planet it really depends on the sun for survival, and it also all life formed on Earth because of the distance from the sun and how our Earth has protected us from the sun. And next time you go outside and you feel the heat of the sun on you, just realize and just remember just how amazing that little star is, and how we are very fortunate to see that, and what we've learned about other stars from our sun. And Before we finish up here, do you guys have any closing remarks or any questions from the um, Facebook chat?
Sure. We did have one question, Derek, that I'll throw out there. Let me find it again real quick. The question was essentially, other than eclipses, are there other ways that we can see the corona of the sun besides an eclipse?
Not on Earth. No, that's so here on Earth. We're really fortunate to have a moon that is the same angular size of the sun in the sky, to where we block the light of the sun to the point where we can see the corona. Now, if we have spacecraft that use what we call occultation disks, basically they're disks that go in front of the sun that allow us to. That's what Parker Solar Probe is going to be utilizing. But here on Earth, the only time you can see the corona is during an eclipse.
Yeah, it's amazing. I think, Frank, you had mentioned maybe at the beginning of the show, when we see the sun, it takes 8 minutes for that light to reach us. But, all that energy that begins in the core, it took hundreds of thousands of years to reach the surface of the sun. So really, you see the sun in the sky, you're seeing as it was 8 minutes ago, but what you're really seeing is light that began its journey around the time Homo sapiens first appeared in Africa. I mean,
That's right.
And
that is
sometimes
amazing.
millions. There could be millions of years of time for these photons to travel from the core to the photosphere.
Yeah, there's just so much stuff they have to bounce around on inside the sun on their way out that it just takes a long time for them to randomly work their way to the surface. And yeah, these are ancient photons that we're actually seeing from that star that's right next door.
Now, I have a question for you, Frank. In Star Trek's Generations,
I can tell you all about that.
you blew up the sun or the star like the guy did in the movie, we would actually still see the sun shine, depending on how far we are from that star. It wouldn't be instantaneous like we saw in the movie, right?
Yeah, that's true. They got that wrong. It would take time for that event to actually reach us and affect us. So
Wait, you're telling me science movies aren't always right? Sci-fi movies.
Star Trek's better than
sci-fi.
most,
Yeah,
Like,
that's true. That's true. Yeah.
Speaking of science, I actually got an answer for why calcium filters are a thing.
Ooh.
All right.
It turns out, let me share my screen here. I found a paper. Check it out. If you look at the spectrum of the sun, it turns out that the darkest absorption lines are actually in the calcium band. So the reason we use calcium filters is because it gives us really pretty pictures. It has a lot of contrast. There's a lot of stuff going on at that band. So if you want like a really natural looking picture of the sun, calcium's where it's at. So now you know.
Great. Thank you, Frank. Yeah, that's how it is. Spectroscopy is the study of the spectra of in astronomy, and actually we had a program last night about Henrietta Swan Leavitt, but the other one of the other women astronomers at the time, Annie Jump Cannon, did a lot of study on spectra of stars, as well as Antona Mori. She did some research on the spectra of stars. So yeah, by using these different spectral lines of different elements, we're able to really get a picture of the universe. And so I think it's just fascinating that we can learn all of this stuff about the universe by just its light. That's the coolest part. Light. Yeah. So
yeah, these spectra are like a fingerprint for these different kinds of stars. There's just so much information baked into that, and it's a good reminder of that.
Exactly.
DNA of a star.
Yep.
Well,
Cool.
well, fellas, it has been a fantastic night. I know, we've just been blinded by the sun in many aspects. There we go. Yeah. I want to thank all of you that are tuning in right now on Facebook Live for joining us tonight for our episode about the sun. So hopefully, we'll be able to, we're actually thinking about actually hosting an event later on where we'll be actually setting up a telescope to look at the sun both through white light and hydrogen alpha. But we do have an event that's coming up on June 20th. We are also partnering up again with the Smithsonian as well as other observatories around this country for another national astronomy event, but this time it's all about the sun. So we're going to be setting up a solar telescope that day. I believe we're going on at 10:30 in the morning because that's when it's really nice and sunny in Florida usually. Before we get those afternoon thunderstorms this time of year. But we'll give you more of the details once they are firmed up. Right now, we're currently still working on the draft on the information for it. So as soon as we get all the information from them, we'll be sharing that with you on our Facebook page. Anyways, yeah, so we are going to be continuing our virtual star party next week. If you have any suggestions for episodes, we're actually, because of our weather, we're becoming not reliable. It's not reliable enough for us to just hope for clear skies. So we want to hear from you on suggestions for future episodes. So if you can leave us a comment or send us a message or an email at planetarium@seminolestate.edu. We would love to, we usually meet weekly to discuss our ideas for star parties. So we would love to hear your opinion and what you would like to hear. So Justin, do you want to, before we end, do you want to talk real briefly about our event next Thursday? What we got going on next Thursday?
Oh, yes. Thank you. We actually have an awesome guest that'll be with us, a analog astronaut. Dr. Cyan Proctor will be joining us from Phoenix, Arizona, and she has got some amazing things.
Uh-oh, Justin, you're being sucked into the black hole of death. Uh-oh.
Oh no.
We've lost
He's back.
Justin.
I think he's
Am I back?
Yeah, you're back. You went so fast that, you know, anyways. Do you want to go through that again real quick?
Sure. Dr. Cyan Proctor, who is an analog astronaut, will be joining us on our Thursday show, June 11th. And she's going to tell us all about her experiences. An analog astronaut, they help NASA and scientists understand the human element of space travel, of our bodies we're not robots, right? We're complex machines, and we need to eat, and we need to sleep, and we need to poop, and all of these things that we go through, they study. And so she's going to tell us about her experiences doing this in the deserts of Utah, simulating Mars, in a scuba environment, in very, very cold environments. And so really excited to hear some of her stories.
Oh, the solar flare got him again.
Solar flare got you, Justin. You got hit by a solar flare again. Oh, well. Well, I think hopefully everybody got that information. It's June 11th at 7 p.m. Eastern Time, Facebook Live. We'd love to see you out there for that event. It's so weird to see Justin.
That's a really unfortunate way you froze there, Justin.
Well, hopefully he joins us again.
Yeah.
Anyways, I want to thank you all again for being out here for this evening's virtual star party, and we look forward to seeing you again in the future. So be sure to follow the Planetarium as well as the Central Florida Astronomical Society. And it looks like it looks like I got Justin for good. All right. Well, thank you, Frank. Well, Justin, hopefully we'll pop on again, but hopefully, again, we'll see you all next time. And until then, clear skies to you, and stay bright as just like the sun. All right. So take care, everybody, and we'll see you next time.